Hello everyone, welcome to the third lecture of the Introduction to Deep Learning course at TUM. Today we're going to talk about the introduction of neural networks based on some of the things we have now learned already in the previous lectures. So we have looked at some machine learning basics, meaning that, what is a learning problem? We have a training set, we have a validation set, we have a test set. And from that data that we use during training and validation, we hope that we can, train and find hyperparameters for a model. I would like to do a very quick recap of the previous lecture before I'm jumping right into the neural networks itself. So in the previous lecture, we talked mainly about linear models actually, and we talked about the basics of machine learning. More specifically, we talked about linear regression. And the linear regression is a supervised learning method where we would like to find a linear model that is being fitted to some sort of samples of data points. And more specifically, if you're looking here again, these samples, let me see if I can show that. We have here the y values is our respective target values and x are our respective sample input values. Each of these orange dots here are basically training pairs. And what we like to find is we like to find this line here that is defined by all the thetas. So in this case, we have a d-dimensional vector of thetas. And we would like to define our thetas that are being applied to the respective input channels of the input vector x, right? And the idea of the linear regression model is that we formulate like finding this line as an optimization problem. In this case, it's a linear problem because it's a linear regression problem. And then we can use this line later on at test time and can make predictions for newly seen, for sample points we haven't seen before. And after linear regression, we talked a little bit about logistic regression. So the difference here in the logistic regression is we have this form of a loss function, right? We have our yi's, these are our targets, our ground truth values. We have the yi heads, our predictions. And then we have respectively the log likelihood of our predictions correlated with the respective ground truth labels in both the positive and as well in the negative case here. Now, the cost function of the logistic regression is defined by this sigmoid function here. And the sigmoid function acts as a nonlinearity, and we'll later see today what we mean by nonlinearity. And here we have as input to the sigmoid, we have the linear model, xi times theta. And the idea is the sigmoid is kind of squashing our output between 0 and 1, meaning that we can interpret this score function as a probability because it's squashed to 0 and 1. Okay, and the idea of the logistic regression was that we're now going ahead and we can actually optimize for theta such that we minimize the cost function, and the cost function in this case goes over all the training samples n here, and we have the respective ground truth of yi here respectively. Now if we're comparing linear and logistic regression, we can see that, well, like if we have a bunch of samples here and we have a bunch of samples here, linear regression would just simply fit this line here to the middle, right? Like it's a linear model, we can't do anything else. So as a result, in this case, what you get is you get also predictions that actually exceed the range of the function values here of the training samples, right? So if you're talking about things like classification, that's not necessarily ideal, right? Because for classification, you would get values here that are beyond, let's say, a probability value of 1. And here, if you're looking at the logistic regression on the right-hand side, we have the property that I mentioned because we have the sigmoid functions. So these predictions here are guaranteed to be within 0 and 1, right? Because we have the sigmoid function that maps it to that value interval. And yeah, so basically, if you're talking about simple models, linear regression is a very basic model that can often be used for some basic regression tasks, and logistic regression is kind of a basic classifier in a sense that you can already interpret the output as a set of probabilities because we have the sigmoid function. Now, we also talked a little bit about obtaining the model. if we want to obtain the model, we have, on one hand, we have data points, right? These data points are being used, are being fed into a model. If it's a linear model, we just have x times theta, right? That's the easiest one. If you have like logistic regression, we would do x times theta and then put it into a sigmoid. And based on that, we're going to get estimations, right? You're going to get these estimates, y hat, and we're comparing the y hats with the respective ground truth labels. Again, this is the formulation or the symbols we're going to use throughout the course. We're typically going to have y hat is our output score, y is going to be our ground truth, theta is going to be our model parameters, and x is our input. Now, how we compare y and y hat, that is defined by the loss function, right? We have seen simple L1, L2 losses. We'll talk a little bit about this later today. We've seen the binary cross entropy loss. There was a basic classification loss that we've seen last time. But the goal of the model in the optimization is we want to minimize this loss function, right? And so we kind of update the model parameters through an optimization loop here. And if we are talking about linear score functions, this whole problem is relatively easy in a sense, right? Because our, by the way, when I'm talking about score functions, I mean these estimates here, right? This is what our estimates are giving us. So if we're talking about linear score functions, I mean it's simply a matrix vector product, right? We have the weights times the respective input vectors. We're gonna get some scores. And this linear score function is essentially linear regression, right? That's the same thing what we've seen. So throughout the next n lectures, I'm probably going to use this more or less as a synonym because it's eventually what will lead to a one-layer neural network. Okay, if we're using a linear score function as the one we have just introduced in the last lecture, we're going to have this kind of form what I mentioned, right? So we have f is our output of the score, x is our input, and w is our weights. And the goal is we want to find the weights. So let's say we want to do something like this for image classification. Image classification, here I'm taking a very simple data set. That's the SciFar 10 data set. And what I would like to do is I would like to find the optimal weights, w, that find me good scores to map to these 10 classes here. So SciFar 10 is a 10 class classification problem. So we have 10 different classes and we like to get the optimal scores such that I'm predicting the right class for a given input image. And the input image is a relatively low resolution. Don't want to go into all the details, but SciFar 10, if you're doing a simple classification problem, is a good data set to look at. Yeah, it's relatively small, it's relatively low resolution, and it only has 10 classes and the objects are centered in the middle, so that makes it a little bit easier. But the interesting thing here right now is, this is a data set, what I mentioned is, it's basically having the object in the center, right? So it only has one object and that object is in the center of the image. So it's something like this here. Here you can see it. Now, if we want to find the optimal weights with respect to linear score function, right? This is what we want to do right now. We can visualize the weights here. And this is a visualization here of the weights. And what we can see is our optimizer will try to find kind of characteristics that classify certain things as a given object. So let's see here. I wanted to look at this example here, right? This is a car label. And I can see kind of this car shape here, right? So now I'm thinking about how do we actually get to these weights that kind of look like a car? Well, in theory, it sounds kind of good because that means we're kind of extracting features that represent cars. Or in other words, if we're finding an image like that one and we're multiplying it with that weight matrix, then we would get a high score function, which is what we want. Because if the score function is high, we would associate that class label in the prediction. Now, the interesting thing is, this is not so clear for all of the classes. And I would like to talk a little bit about why we're ending up with these specific weights when we're optimizing in this linear least square sense. If you're optimizing for a linear least square sense, that's essentially an L2 optimization problem. And the optimal solution of an L2 optimization problem is going to be the mean. And the mean is just an average. So in principle, what we're getting here is that kind of tells us, oh, the average car labels look something like that. It's kind of just taking this average blur for all the cars, right? We even know a little bit more. So we know that cars are kind of centered around this because that's kind of what this average solution for the weights is going to give us. We also know, oh, this is a slightly reddish tone, right? This is more or less reddish. So in our data set, we probably can expect that most of the cars were red. So in other words, now if I see an image that has kind of this shape, right, it's kind of reddish, then I will get a high score function in my classifier based on this linear score function, will actually assign it a car label. Let's have a look at another label, another class. Let's have a look at this one here. So this one is a horse. And what we're seeing here is we kind of see the shape of a horse, right? So what's very interesting is we see kind of a head of a horse here on this side. And we see kind of a smaller head on this side here. Well, it's kind of hard to see, but there's it's also a little bit of a head. So in this case, you can expect how this linear score function came to place was that we have a lot of horses that look to the left, and we have a few horses that look to the right, right? Because this left head is a little bit more pronounced than the head on the right. You can also look at the other classes. Let's see, this one is a dog. It's very difficult to see now. And the reason why it's now getting more difficult is because like only for cars and horses, we have kind of these regular patterns that are very easy in a sense to average and to find good weights for. If you have more variety, then it gets much more tricky for this simple function, for this linear function here, to express or to find good weights that kind of fulfill all the solutions. And I would like to make this a little bit more clear. If you're going now away from SciFar 10, which is a relatively easy data set that is centered around the objects, to a more complicated classification data set like ImageNet, and if you're doing the very same evaluation here, again, we're trying to find optimal weights, W, and with the linear classifier here, with this linear score function, you're going to get results that look like these ones here. And at this point, you can't really spot anything in the images here. This is the same visualization here. And the reason why that is the case is because now in ImageNet you just have much more variety. So it's not so easy anymore to find these simple distribution of the weights. In a sense, if you think about it, the easiest classifier you can do is kind of this cascaded if statement. So if I have red color here in the middle, right, then maybe it's a car. Now, the problem is as the images become more and more complicated, this kind of cascaded if statement doesn't work so easily anymore. And the same counts for this classifier here based on the linear score function. This linear score function at some point just doesn't do the trick anymore because we have too much variety. And we can also visualize this again when we have, a simple artificial distribution of data samples. Here on the left-hand side, we have kind of a bunch of circles, we have a bunch of triangles, and we want to find a decision boundary here between those two classes. Now, here in this case, we can relatively easily find a linear decision boundary, right? That's very straightforward. Now, if we have something like this here, you can already see there's no single line in this case on the left-hand side that would kind of separate them completely apart. And you can see very quickly that these linear score functions are simply not powerful enough to represent the things, the complicated distributions in our data sets. And images is a very canonical example because images turn out to be very complicated, in fact, right? Like we have, again, we saw this in the very first lecture. We saw a lot of different, things happening there in terms of occlusion, lighting changes, and so on. Okay, now, if we are starting off from this linear score functions, and I think we still need to keep this in mind because that's kind of the basis now for what we call neural networks later. But the question is, how can we make these ones better, right? And the main problem that we're going to face is that this weight matrix W is not expressive enough, right? We would like to have more flexibility in order to represent nonlinear functions. Now, let's say we do an easy trick. Let's say we simply add another weight matrix. We have one weight matrix, we just add another weight matrix, and so on. So what we could do is we have a function f here, right? That's the score function we had right now. And we're just multiplying it with another weight matrix. So in principle, right, we have two weight matrices right now. So we doubled the capacity of the model, assuming the weight matrices have roughly the same number of parameters. And we get a function f hat. Now, in principle, that makes the function more complicated, right? Because now we have two weight matrices. Now, unfortunately, what we can do is we can just, multiply it out. We have w2, we multiply it by x, and we get f hat. Now the problem, unfortunately, if you do that, is this operation is still linear. And the reason why it's linear, I can simply multiply the two weight matrices, I get a new weight matrix w hat, and that matrix can be multiplied to x again. Now the problem is this alone is again a linear problem. So the issue is I can add as many weight matrices as I want, I can always reformulate it as a w hat. So simply adding more weight matrices is not going to do it. So we have to do another trick in between. And the solution is we want to add some nonlinearity. So rather than just adding this matrix here or multiplying this matrix, we also add some nonlinearity in between. And this is essentially what neural networks are. So if we're starting off again from our linear score function, f is equal to w times x, this is in a sense a one-layer neural network, aside from like possibly as like a sigmoid or so at the end, but in principle that's a one-layer neural network. And now what we can do though is we can have a nesting of functions, and this is what the neural networks do. So now we have this w1 times x, that's essentially what we had before. We introduce a very simple nonlinearity, just taking a maximum function. So if we're taking the maximum between 0 and w1 times x, there's going to be a discontinuity around 0, right? Of course, I have this maximum function. And I'm going to multiply this output here with another weight matrix w2. And this is my f now. Now I have kind of two layers. The first layer is defined by w1, and the second layer is defined by w2. Now the advantage here is I cannot simply go ahead and multiply f1 and w2 because there's this maximum function in between, and that is a nonlinear function, so I can't express it as another matrix form. And I can continue this idea basically. I can go ahead and say, now I add a third layer. Again, first maximum w is 0 times x, maximum is 0, then times w2, again a maximum, times w3. Again, I cannot multiply these three matrices here together because I have these maximum functions in between. And that makes the model nonlinear, and I can add basically more weight matrices without collapsing to another linear model. There's various types of these nonlinear functions that we can use. Here, for instance, I can use a 10H, I can use a sigmoid, seen the sigmoids before. And essentially what neural networks are is we can have up to hundreds of layers like this. We're going to add a little bit more structure later on, like how to add them and how to structure each layer then. But in principle, that's the core idea of the neural networks, that we're now going ahead and saying, instead of having a single weight matrix, we're going to have multiple weight matrices, and we're having nonlinearities in between. Okay, that's basically it. So let's have a closer look in terms of the neural networks. Okay, at the very beginning of the lecture, we started talking a little bit about the neural networks, right? About the history. And in a sense, that's kind of what we've done right now too, right? We started with this linear classification, or linear regression, logistic regression, and we use kind of this sigmoid as kind of our first nonlinearity. And that's basically what people have also been experienced over time, right? They have also said, oh, yeah, we're going to start with this very simple linear model, and then we're going to make it bigger and better. And one problem here is this XOR problem that I would again urge you to have a look at. It's basically the same issue. In the case here, if I have this distribution of data samples, I cannot have a linear function that separates both of them apart. So the single perceptron is not good enough for that case. Okay, so if we're talking about neural networks, right, what we want to do right now is we want to develop these core functions that we've just mentioned. And we want to, for instance, find these decision boundaries, such as, these triangles and these circles, and we want to separate them apart. And the idea of the neural networks now is that we can have decision boundaries that are very, very complicated in order to separate out two types of images, right? and do our respective classification. And the challenge here is that this is, of course, not just a 2D image, right? This is not just a 2D function here. This is going to be a very, very high dimensional function to begin with. And you can see this already, that the input of our function here would be an image, and an image is already like, I don't know, I have 3 RGB values per pixel times the number of pixels, and that's the input dimensionality. So the input dimensionality gets already pretty high. And that's the challenge that we have to deal with. But now I would like to introduce a little bit more how we typically structure neural networks, and then later on how we use them in practice also. Okay, so what we have just introduced is essentially this nonlinear score function f, that is this nesting of functions, or nesting of layers as we call them later. And we've also introduced like the simple maximum function as a nonlinearity. We'll later see also what that means and why it's a max function, not something else. It could be something else, but a lot of people nowadays actually use these max functions. Now, if you're talking about the image classification problem, right, what we would do here is we would take this function, the score function, it's a nonlinear score function, and the idea is we're feeding in an image, right, and we have a bunch of labels for the image, a bunch of classes for the image, and we would get, for every class, we would get a score. And then based on the highest score, we would just say, oh, that's the class. So in this case, we feed this image as input. We feed this image here. This image is becoming X. We multiply it with W1, taking maximum, W2, and so on. And eventually, we're going to get an n-dimensional output vector here, where this n would be the number of class labels that we have, right? And we just rank the top n ones. We typically take the best one. And that's the label we're going to assign eventually, right? Okay, this is an example here on Cypher 10. Again, on Cypher 10, this score function would have 10 dimensional outputs because we have 10 different class labels where we have to compute scores for. Okay, you can also visualize these activations, as we call them. This is something we're going to talk a little bit later about. But what I've shown you before was this visualization of this linear model where we just visualize the weights, right? You can do this for a neural network too, except now you can visualize it at every layer or at every step of this function here. So, right, so visualizing the W's tell you kind of, oh, what is this layer sensitive to? Like what kind of features can you extract from them? All right. Okay, so this is essentially a neural network. Now we're going to adding a little bit of more structure, and you will also see this more and more often when you're reading literature. Then you often see how people like drawing neural network architectures. So what we have right now, we have a one-layer neural network, right? That's just our linear function, linear score function. F is equal to W times X, right? As input, we have X. X is our image. That's 128 times 128. In this case, it's just a small resolution image, right? In this case, we have a 16,000 dimensional input vector. That one is multiplied with X, right? And we have F, that's our score function, which is in this case 10 dimensional because we trained it on Cypher 10 that has 10 different classes. Again, this 10 here is number of labels or number of classes that we have. So number of different class labels that we have. If you're taking a two-layer neural network, now what we do is we have, again, this image here. We have a set of W1 weights. We multiply this image with that, then we're going to get some sort of intermediate state here, and this state is going to be called a hidden state or hidden layer, and that is being computed based on this weight matrix W1 and based on the input, right? And based on this max function. So we have max 0 W1 times X. And then we have W2 that is multiplied to this H, and then we're going to get the scores again with the output. Now, if you're talking about the structure, why is the structure pretty useful? Well, what we're going to learn right now is we want to divide everything into layers. Like everything we're going to talk about is going to be layers because we're going to have a lot of them and we want to kind of have this abstraction that it's very, very easy to talk about. The next thing, we want to talk a little bit more about this H here, what this hidden layer or this hidden state here means. Because that's going to be something what we typically call a feature vector that is being extracted from the input data, right? And it could have features at different layers, right? Not just the first layer, could have any layer. In this case, we have only one because we only have W1 and W2 here. Okay, to abstract a little bit more, often you will see diagrams like these ones, right? So you're going to have some input layer, some hidden layer, and some output layer. And then you're going to have a bunch of connections between these layers, a bunch of connections here, right? And you have the output layer. Now, what we already learned is the dimensionality here of the input layer is equal, in this case, if we have a classification problem, to the number of pixels times the number of channels per pixel. So it's like 3 times for colors, or grayscale, it would be just 1 per pixel, right? So in this case, we have like these 16,000 dimensional input layer. And then we have this weight matrix W1, we multiply it with the input, and then we get this hidden layer. In this case, we have 1,000 dimensions. This is an arbitrary thing that we just made up to say, oh, we just have a 1,000 dimensional feature descriptor that kind of describes or abstracts already what's in this image with respect to the classification problem we're training it on, right? And then the output layer, in this case, we have like these two nodes here, right? We would have 10 if we have 10 classes, right? Okay. What I would like to tell you is a little bit more about visualizations like these ones. In this case, what you see often is that these things here, these are typically called, these nodes are typically called the neurons, right? Like the neurons is going to be, like this would be a neuron, this would be a neuron. We'll later see what this mathematically means. I mean, basically, it does this matrix multiplication, does the maximum, right? This is what the neuron does. We have, for every layer, we have a couple of neurons, right? And then these neurons are connected to the next layer. If we're having something like this one here, we would have a densely connected network, meaning that everything from one layer that we're feeding in is connected to everything that we're getting out of the next layer. It's called a fully connected layer. We'll later see, there's alternatives, what you can also use. Okay, so this neural network is this net of artificial neurons. I mentioned already that these things here in the middle, they're called the neurons, right? And we already know what the neurons are going to be like. So let's say in this case we have 3-dimensional inputs, x1, x2, x3. One of these neurons takes all 3 inputs of the previous layer, in this case of the input layer's input. What it does is it computes, it has a set of weights, w times x plus b, and it computes some output that it forwards to the next layer. And these outgoing arrows here are all going to have the same value, right? One neuron puts the same value as output, but it's being fed in to a couple of more neurons on the next layer. And mathematically, it's actually pretty easy what we're doing here. But what I would like you to look at is these indices here. This is very important typically, right? So W is our weights and B is our biases. Biases we've seen already, but this is nothing else but a linear model here inside. F is going to be some nonlinearity, such as a sigmoid, such as a maximum function, such as a 10H. We'll talk about this in a second. But again, look at these indices. 0 is going to be, that the first 0 here is going to be which layer we are at. This is W0 here. All of the W's are W0. And then we have neuron 0, neuron 1, neuron 2, neuron 3, right? Each of these W's, in this case, is 3-dimensional, right? Because we get 3 inputs, x1, x2, x3. We're multiplying with x here. This x is also 3-dimensional. And this b here is 1-dimensional, right? This b is just a single scalar. So we're having this dot product here plus a scalar. This gives us a scalar value. We're feeding it into f, and f is feeding, and then f is computing the nonlinearity, right? And again, note that every neuron here has a different set of w's and b's. How many b's do we have? Well, I said this is a scalar, right? So we have 1b, 2b's, 3b's, 4b's. We have 4 neurons, so we have 4 b's. And here we have 3 neurons, we have 3 b's, right? And the w's is going to be an independent set for each neuron, and number of arrows that go in here into this neuron times this tells us the dimensionality of W00. Like this is 3-dimensional, this is 3-dimensional, this is 1-dimensional. How many weights do we have in total? Well, in this case we would have well, this one has 3, 3, 3, 3. So this is 3 times 4. It's 12 weights in this layer, right? This guy here gets as input 1, 2, 3, 4 arrows. So this is 4-dimensional plus 1, right? So we have the weights here is going to be 4, 8, and 12, right? So we have 3 times 4 times 4 times 3. This would be 24 weights. Here we have a few more weights. This is another 3, right? So we have, in total, we have 25 weights here, plus the biases, which is 1, 2, 3, 4, 5, 6, 7, and 8, right? So this will determine the total capacity, the total number of weights in this network. So the reason why I showed this very simple example, you can simply look up the indexing again. And I think if you understand the indexing, then you know how many weights and how many biases you're going to have. Again, these are just simple linear functions in each neuron. And then you have a nonlinearity around each neuron, kind of, right? And these can be computed independently. And if you're checking how many weights you have, you simply can count the arrows too. It's a bit harder here. And you can see very quickly if we have more complicated neural networks, you will have a lot more arrows. You have a lot more connections, and because of that, you also have a lot more weights. How many biases do we have here? The biases I can count. That's easy, right? I have 1 bias, 2, 3, 4, 5, 6, 7, 8, 9 biases in this layer because I have 9 neurons. How many weights do I have here? It's actually also good, right? It's 1, 2, 3, 4, 5, 6, 7, 8 neurons times 9 neurons. I simply multiply that and I add the biases, then I know the number of weights, right? Because everything is connected to everything between the layers. You will often see visualizations such as these ones. Typically people often, they don't even draw the connections anymore. They just assume, oh, everything is connected to everything. That's kind of our layer by layer architecture. But mathematically, we haven't done really a lot here, right? Like all we've been doing is we have a single linear model per neuron, right? We have a nonlinearity around it. That's our, and that's basically our score per neuron that we're computing. And then we're just connecting it all together, right? We just have this network of neurons, this neural network, right? That's all what it is right now. We will have a little bit of discussion about these activations, and I mentioned a few of them already, right? We have seen sigmoids, we've seen, like in the last lecture, we've seen the logistic regression. Logistic regression is nothing else but a one-layer neural network, right? You could append more layers like this. People have done this exactly in the same fashion with sigmoids as activations. You can use 10Hs as activations. One very popular example is ReLOs recently. And by recently, I mean in the last 10 years, a lot of people have been using ReLOs. We will tell you a little bit why or why not these are good decisions or not, right? We have leaky ReLOs. Leaky ReLO is like, it's a maximum of 0.1x times x. There's a parametric ReLO. Then we have an alpha here. There's max outs, ELOs. We'll go into this more detail. I just want you to be aware of it. There's different shapes of these activation functions, but typically, as you can see, they're relatively simple. So each neuron itself does a very, very simple mathematical operation, right? There's not like a lot of math going on. It's typically always this linear function first, and then you have one of these activation functions. Again, activation function is by definition a nonlinearity. Otherwise, it wouldn't work out. So this is a neural network. We started by looking at the trivial case when we just have W1, W2, W3. If you just did it this way, we could collapse W1, W2, and W3 into a single matrix. In this case, we would unfortunately get still a linear model, and because of that, we need these activation functions. That is very, very important. This is, if you understand why we need activations, then you can understand how to make the models bigger. We have the nonlinearities, we have more expressive models with more capacity, and because of that, we can learn better features for our respective tasks that we want to do, such as image classification. Okay, let's have a look at the organization again. So the reason why we're organizing neural networks into layers is at some point it becomes very tedious, right? The same way why using like matrix operations and stuff like that. We want to abstract from low-level math to higher level concepts in a sense. And this is kind of why we're having these layers. There's a few other reasons around it. The nice thing about the layers is we can always start with some input layer, such as an image, such as whatever attributes we have or whatever features we have for an input. We then have a bunch of hidden layers, and then we get a score function, an n-dimensional score function in the output layer, right? And this is how we organize the network. Currently, why we did this is, well, it's very easy to abstract the math, right? I can go ahead and say all the low-level notations I got rid of, and I still told you the architecture of neural networks. And the nice thing is, like, each of these neurons per layer, they have the same structure. Again, they are a linear dot product, basically. And then we have an activation function around it that adds the nonlinearity. That's always the same thing. And within one layer, at least for the most part, we will later see very complicated architectures, but for the most part, within one layer, all of these neurons within a layer are going to be the same, right? Actually, for most parts, even between layers, they're going to be the same. But being the same means they have the same structure, but they have, of course, independent weights being assigned. We'll talk about the assignment of the weights and how to get them. This is, again, like the model optimization. That's what's happening while training the neural network. So there's another reason why we organize the neural networks into layers. I'll get to this in a second. And the main reason is we actually can use certain compute operations very efficiently on the GPU. And we can also do this optimization relatively easily when this is done by layers. This is like basically when we're doing like gradient-based optimization. Computing the gradients is typically also done layer by layer. And that is something that is very easy to do when we have this abstraction. I would like to give you a little bit of context of biological neurons. I'm by no means a neuroscientist, and this is not the expertise here that I'm bringing to the table. However, I would like to say a lot of times people make comparisons to biological neurons, such as neurons in our brain. And of course, there is certainly some similarity, right? In our brain, we have these neurons, right? We have cells, we have a nucleus, we have a cell body, right? We have these axons, and we have these axon terminals. So in a sense, what's happening in the brain, right? We have these nerve cells in the brains, these neurons, and what they do is they're getting here as input through these dendrites. They're getting electrical signals here as input. And then the cell is kind of summing up, aggregating these electrical signals. And if there's kind of enough stimuli on a given cell, it will forward another impulse, right? It will carry away to the output kind of the cell, these axon terminals. And these ones will be again fed into new neurons, right? And we have very, very many neurons here. And so in a sense, you could argue, well, this is, if you're comparing this to what we just discussed, this is very similar to what we've discussed right now, which is like, we have kind of the cell body that is doing this linear model, W times X plus B, right? That's our linear part. Then we have the nonlinearity F, our activation function, and then we're feeding it forward, right? Again, here input, X0 times W0, it's the synapse, right? Then we have the dendrite that feeds it into the cell. And then if it has an activation function that it forwards it to via the axon to the next cell, right? And from a pure abstractive standpoint, that sounds very, very similar, right? However, there's a lot of fundamental differences, and I think this is a very important point that I would like to have everybody who is watching these videos and taking the class to take away. And the main thing is, this is a very simplified abstraction of what we are currently using in machine learning. Like what's happening in an actual nerve cell, an actual neuron in the brain, is something we don't even fully understand right now. We know there's electrical pulses, there's going to be some function involved, but we don't know exactly how the function works. Also, the connectivity between the cells is significantly more complicated. So we're not even close right now to understanding what's happening here. We're just abstracting a very simple model, and we're saying, it is inspired by it, right? And if you're comparing a neural network versus the brain, yes, it is inspired, but we're not even close to the complexity of what's happening right now. And I understand there's a lot of hype in the media, a lot of things what you can do with neural networks, but to a level where we have human intelligence, these networks that we're doing right now with these building blocks that we're going to introduce also in this course are very, very far away and not so well understood from a biological side, right? We're just not there yet, and we're not even close to the capabilities. And in fact, most of the neural networks we're going to train, even we're very proud of them, are actually still at the very beginning and very, very limited. And sometimes it's surprising like how limited they are actually in practice, right? And we'll go into that. So one thing I would really like to take everybody away is don't tell anyone, oh, we're making like, I don't know, like Terminator-like robots and stuff like that. We're not doing that. We're very far away from that. If somebody asks you what is deep learning, you should say something like, oh, we're trying to find mathematical models, we're optimizing for weights, and based on that, we're explaining some training set, and then we're hoping that it generalizes to a test set. That's what machine learning is today. You could argue there are similarities between the biological means and so on, but again, we're not even close to what the human brain can do. This is just not there yet. And I understand, like, there's going to be some news report from here and there, like, oh, neural network outperforms human vision, human perception, and stuff like that. But I wanted to make it very, very clear. We are nowhere near close to human intelligence at this point. I mean, it's very simple, right? We had calculators 10 years ago that were faster and better than human mathematicians, just adding some two integer numbers. But they're not more intelligent than the mathematicians, right? That's just it's a very easy analogious example that you can look at. Okay, so while that being said, I would like to go back actually to the content of the class, to the artificial neural networks, right? So again, this is something, a very important drawing here, right? You see the building blocks of the neural networks, you see the neurons, you see the inputs. And again, whenever you're thinking about a neural network, check the indices here, right? Check how many weights do we have here per neuron, right? The weights and the biases are the unknowns we're gonna try to find. We have the input and we have some output, right? That's very important, so keep that one in mind. So if we're taking now the summary of the neural networks, what we would like to do is we taking some training data, right? We have the training pairs, xi and yi, our pairs. X is the input features, yi is the respective ground truth labels. Y could be a class label, could also be some regression problem we're trying to figure out, right? Our goal right now is we would like to find the optimal weights W such that we're minimizing, or we're getting the best prediction. So we're trying to replicate kind of what our training data would do. If you're putting X in, we're getting Y out. That's what we want to use in order to find W. I'm making a small mistake here. We're not just doing W. We also, in fact, so these B's, they're part of the W. So the W's and B's are both being optimized. So the biases and these W's are being optimized. So part of this weight vector, we have both biases and weights. I'm already talking a little bit right now. What we're going to do now is we're going to use some version of gradient descent, specifically stochastic gradient descent, and we want to use that optimizer to minimize loss functions in order to find the optimal weights, right? Find the optimal weights that minimize the loss functions such that the training data is best explained. And then the hope is, right, that if we're seeing new samples here, that our model is going to generalize. And then we need like regularization and stuff like that. Okay. Yeah, so how do we do that? Now we should talk a little bit about how to find the optimal weights here, right? In the last lecture, we've already seen, oh yeah, we want to do some optimization process. And that's what we're going to talk about right now. How we do evaluation of neural networks, meaning that we have a set of weights already given, how do we evaluate it, and then how do we get the gradients in order to find the weights. One important thing here is the computation of gradients, and this is also one reason what I mentioned why we kind of decomposing the network into layers. And there's an algorithm called backpropagation, which we're going to talk quite extensively about in order to find the gradients. The idea of gradient descent is, right, we're finding gradients, we're doing gradient update, and so on, and we're iterating until we find a good solution, until we find, of course, the optimal solution. We can't always guarantee that, but that's what we're trying. And Then there's like this way, what I said, like we have this SGD, the stochastic gradient descent, where we have like a stochastic way where we can also do some sort of sampling, but more to this later. I would like to first talk a little bit about the compute aspect of neural networks. And one thing, what you could do is you can see neural networks as computational graphs. And this goes then also like how they're being implemented on a computer, on a graphics card, and so on, possibly, right? So if you're talking about compute graphs, and I would like you to forget neural networks for maybe 1 minute or so. If you're talking about compute graphs, that's a mathematical concept that has been around for quite a while, right? A compute graph is a directional graph where we have matrix operations that are represented as compute nodes. And every compute node is a vertex node, right? And these are variables or operators like plus, minus, multiplication, division, logarithm, exponent, and so on. And these directional edges, they show the flow of the inputs to these vertices, right? So it's pretty straightforward. In fact, this is what every mathematical computer program is doing. When I'm like having program code and stuff like that, typically this is being mapped to a compute graph in a compiler, of course. If I'm talking about a function f of x, y, and z, I have 3 input variables. I have a function f, and I can define this function as x plus y times z. Now, if I'm writing this down as a compute graph, I would get something like this, right? I have x and y as input. I'm representing the sum here. The sum is going to be one node. And then I'm having z as input, and I'm having the multiplication of whatever the sum puts out times z, right? And then this is what our f, x, y, and z is, right? So this is in principle what we would call a compute graph, right? We have directional edges from here to here. We have nodes, input nodes, x, y, and z. We have operators plus multiplication, and we have an output at the end. Now, if you're taking a compute graph like that, it's very straightforward to just use it for evaluation. That just tells us kind of the structuring, how do we do evaluation. In this case, we have a so-called forward pass. So let's say for simplicity, we initialize x with 1, y with -3, and z with 4. Right? If I do that, I just feed in these 3 numbers here in. I'm first passing into the edges, right? My compute graph is just forwarding the values. That's why it's a forward pass. And then we are adding these 2 numbers here together. We're getting here an intermediate value d, which is equal to -2. And then we're multiplying -2 times 4, which is -8. Right? So now what we've been doing is we simply took this compute graph, we took this equation here, we wrote it as a compute graph, and now we could also evaluate it kind of in a step-by-step fashion, right? We just go from left here to the middle, to the intermediate values, to the right, and then we get an output. Okay, so why do we discuss that? Well, I mean, the reason why we're discussing it, neural networks are essentially compute graphs, right? So, and what we would have to do now is we want to kind of abstract and conceptualize the neural networks, like this nesting of these complicated functions, into compute graphs, right? So we have W1, W2, W3, W4, W5. We have these max functions, we have 10H function, we have a sigmoid, and so on. There's a lot of matrix operations, as you can already see. Like this is always a matrix operator here. This W is always a big matrix. And we would like to represent these things as compute graphs for 2 reasons. A, for this evaluation that I just mentioned. And then B, later for the backward pass when we want to compute gradients for the training part, for the optimization part. Okay, but yeah, so long story short, neural networks can be represented as compute graphs, and that's practically what we're also doing. That's what all the deep learning frameworks do today. They represent the neural networks as compute graphs. You don't just have like a big analytic function, but in a sense you have like this structure of layers that represent the architecture of the neural network. Okay. Yeah, why can it be represented? Well, of course, we have compute nodes, right? These are our operations. We have edges that have the data flow. It's directional. That's very important, actually. In this case, we always have input from the left, typically when we're drawing it, and it's being fed forward to the right. So it can be organized in these layers. One thing to say here is we don't have any loops in here. There's not like, oh, there's one layer from the middle and it goes back to the beginning. There's no loops in these compute graphs, and there's no loops in neural networks. Some people might later say, oh, there's some special neural networks that have like loops and stuff. We'll later talk about it, but no, in practice we never have any loops. Okay, there's various ways how to write the compute graphs down, right? It could be more complicated. This is like a more complicated compute graph. Again, we have various inputs. We have +1 here. We have these intermediate nodes. And eventually we have outputs. Often people are too lazy to write down all the math here, so they're doing it a little bit more simple, especially if the architectures get bigger then. So if you have a very complicated pipeline, you often get up with visualizations such as these ones. So this was a paper from Google a few years ago. This is a set of neurons of a structured compute pipeline, right? And in this case of this compute graph, right, you see, oh yeah, there's some layers and these layers all have meanings, but you don't even see the matrix operations here anymore because people already know these meanings. We'll talk about these meanings in this class, and so far, right now, you might think you might not know them all, but we will learn all of these names in the next few lectures. Okay, the high level idea is this is still a compute graph. It has a lot of layers now. These are hundreds of layers, potentially, if not thousands. But we can very easily like write down these architectures, and that's often what you see also in research papers, that people kind of abstract these architectures away, and that's very nice from a visualization perspective and explaining what's in the architecture, and at the same time we can also efficiently evaluate it. We'll go into this a second, how that works. Okay, the computation of the neural network has also further meaning. So this multiplication of W and X, right, encodes some sort of input information. That's something we're going to talk also in a few lectures about. Basically, we're going to get these features after every layer. And for some special types of networks, we can visualize these features. And they have some visual meaning as well, like an edge detector or something like that. We'll see how that goes. But in practice, these compute graphs, after every layer, you're going to get some feature map. In this feature map, you can do something with it depending on the input in the structure. One specific example, I'm going to have 2 slides very quickly about a very important type what we are looking at. We will look at convolutional layers. So far, we've seen these like fully connected layers, but we will look at convolutions. In this case, the layers are defined by kernels, and then you're going to get more visually meaningful features that like these ones here, right? You're going to have feature maps that look like these ones. We'll talk about this one in a bit. But for now, what's very important is we do have compute graphs. Neural networks are compute graphs. In all the deep learning frameworks, the networks are represented as compute graphs. And now we want to use that in order to do 2 things. We want to do this forward, the evaluation of the network, and then we also want to go ahead and do backpropagation to compute gradients for the optimization. So that's going to take us busy for the next 1 or 2 lectures. Okay, I wanted to very quickly talk a bit about the loss functions. So now let's say we have a network, we can evaluate it, but also we have to check once we evaluate a neural network, is what we're predicting actually reasonable, right? So the neural networks, in this case, what they do is we have some input, right? That's being fed into the neural network, into all of these layers that we've just discussed. And we're going to get some output. And this output is being compared to some ground truth labels, to the targets. And the loss function is going to tell us, are these reasonable predictions, right? And we need a way to describe how close the network outputs are to the respective targets. And the idea here is that we have this kind of distance metric, right? So we have a target, we have a prediction, and there's kind of a large distance here, right? If you have a small distance here, then we have a good prediction. So that's where we would like to go to, and this is where we typically start at the beginning of an optimization of a network. Okay, so the loss function is this measure of the goodness of the predictions, or in other words, it's telling us the network performance, right? Does it do anything reasonable? I would like to talk a little bit about different types of loss function that we're having. Intuitively, right, what the loss function should do is if you have a big loss, the network doesn't perform very well. Or in other words, if you have a classification problem, for instance, if my loss is high, then I'm getting bad label predicted. Right? The loss function is very dependent on the problem. And as we will see throughout the class, this is going to be very, very dependent. It's going to be very, very dependent on the problem, right? If you have some image classification problem, we will very quickly see that L1, L2 losses is going to be tricky, and so on. So that we're going to have, when we have the theory done of the networks, we will talk a lot about what is a good loss function for a given problem. We've seen a few losses already, right? We've seen the regression losses, like an L1 loss is straightforward. Just you have a predicted sample yi hat, you compare it with the ground truth yi label, you take an L1 norm here, and you sum it up over all the samples. Like again, this n here is the number of samples. Typically what you do is you normalize it with respect to the number of samples. And the reason is very simple. Just because your training set grows by, let's say, a factor of 2, your loss should stay the same. It's the mean loss in an L1 sense, but it shouldn't be related on how many samples you have. Of course, you get better estimates when you have more samples, right? But the loss doesn't necessarily grow by a factor of 2 if you have twice as many training samples. Same thing for an L2 loss here. MSE means squared error loss, right? Now we have an L2 loss here. Same idea, except that this is a squared loss, right? These are the typical regression losses. There are some combinations between these two. There's an Huber loss that kind of, when you're close to the solution, you're doing L2. When you're far away, you're doing L1. These kind of things are very commonly used for regression. We did already talk about the binary cross entropy loss, right? That's this yes-no probability loss based on the log likelihood. In this case, right, we have the losses between the predicted labels, the predicted scores. These are the score functions we're predicting. The y is the ground truth labels. And then we can predict how good is our prediction based on this loss, right? So here, if the network says here 0.08, oh, it's greater than 0.5, so it's yes, and it's 0.2, then it would say no, right? This one, by the way, has to sum up to 1. Otherwise, we're doing something wrong here. There's going to be the cross entropy, the generalization of that. Now we can do this for multi-class classification. Now what we have is here we are summing up over, again, if we go here, the sums here over all the training samples. This one here sums also up over all the training samples. And here we have a k, which is over all the labels. In this case, we have 3 labels, maybe more, duck, rabbit, duck, right? And this is kind of just the generalization. So now we have just, instead of having these 2 terms, 1 and 2, we're now having k terms for every type of label. Yeah, that's the cross entropy. We will talk a little bit about the loss functions later, but I just wanted to tell you, oh, these are the common loss functions we're going to use for the optimization. Yeah, so generally speaking, we've already introduced a couple of the notation here. We know ground truth is y, prediction is y hat. In a classification problem, this is a discrete label. These will be score functions, and the loss function compares the two and tells us, well, how close are we? Yeah, and the motivation now is, and again, this is all about optimization now, we want to minimize this loss. We want to make this one small, meaning that if this one gets small, our predictions ideally are getting better. Right? The hope is, of course, we're finding better predictions and then we're getting a better neural network. Okay, now if you're looking at this again, we have initially, we have a target, we have a prediction. Our loss should be high because in this case we are very far away. Our prediction is not very good. So let's say we've chosen a reasonable loss function that tells us, yeah, our prediction is not very good. It should be better. And during training, what should happen is, well, our prediction should get better and our loss should get smaller. We're not quite there yet, right? We want to get even closer. Our predictions get even better. And our loss gets smaller. Now, this is a process that happens during training. And of course, it's totally relying on having a good loss function, meaning that good predictions, smaller loss, bad predictions, bigger loss. We need both of these directions, otherwise we have no correlation. And typically what you're seeing when you're training a neural network, you're seeing these training curves. And the training curves, this is a good training curve, by the way. Here's the training time, meaning that I'm going through training samples by training samples. Again, how we do this, we'll see. But let's say we're training for a while. The idea is that our loss starts high and then gets lower and lower and lower. Ideally gets very low. Right? So here we should ideally make very good predictions and because of that, our loss is very small, right? It would be pretty bad if our training loss went up, right? If our optimization made it worse, if like we're getting like worse predictions than we had before. But ideally, we're getting better and better predictions, and because of that, our loss gets very small. By the way, looking at these training curves, we will talk about this in a lot of details, also in the exercises, because it's so critical to look at these curves. Often, this is the only way to evaluate what the networks are doing. If you're looking at this is a plot of the loss with respect to the training time, we can also go ahead and we can plot the loss curves against the model parameters. So now what I'm going to do, I'm going to take a single parameter theta, right? Of course, I have many thetas because it's an n-dimensional model. I can use one theta and I can plot the loss function. This is my loss with respect to the ground truth from my predictions. This is y hat basically, but in dependency of theta, right? This is the variable here, theta. If I change theta, I will get a different loss, right? And based on a given theta, I want to figure out, based on a given training sample here, I can check this loss out. I can plot this this function here, and I can find the optimal theta where the loss is the smallest. So ideally, I would like to choose a theta like here, right? Maybe here. That's a little worse, but maybe here, right? And the way you're doing this is you're just checking, oh, my initial theta. I'm trying to figure out how can I move my theta on this curve here around in order to get a small loss. So I would go down this hill. And this is what gradient descent is going to give us, right? So again, just for notation sake, we have a loss function, right? Our loss function is between the predictions y hat and between our y's, our ground truth labels. The loss function is then defined by our score with respect, so it's from a given input sample x, but parameterized by theta. And the neural network is our computation or our compute that gives us the score functions, right? Okay, and the goal is then to minimize theta. So optimization-wise, we train the compute graphs with some optimization techniques, and this optimization technique will be gradient-based. In fact, everything we're doing with respect to optimization is going to be gradient-based as part of this lecture. I'm not arguing there's no other optimization, but that's just what we're going to stick with as part of the lecture here today. Well, how does gradient descent work? It's actually a pretty simple method. If this is a 2D function here, right, we just have an initial starting point theta. Our gradient points downwards here because the function gets smaller here, and the function is our loss we want to minimize. So we want to follow the negative gradient here. The gradient is of course positive, but we want to follow the negative gradient. That's why it's gradient descent. Okay, how do we compute it? Well, gradient descent is following this formula here, right? So we have here our initial theta. This is our updated theta, which is computed by taking the initial theta, taking the gradient of the loss function that we just described, times an alpha. And our goal is we want to find the optimal theta such that we minimize the loss function. Well, if in this case here, right, we can just say, well, this is pretty small here. That's where we want to go. I know that because I can look at the full plot here. But if you have a high-dimensional function, of course, we have to do it always from a local perspective. And local perspective means we computing the gradient here at theta, getting the gradient of our loss function, right? And then just we're doing a step into the negative direction of the gradient. That's gradient descent. Yeah, we just do this a couple of times, so we iterate this process. When do we iterate? Well, until it doesn't get any smaller anymore. Okay. The one thing I've just introduced here is the small little alpha. That's the step size of gradient descent. Like how far do we step down? Do we do faster, slower, and so on? In standard optimization, this is just the step size of gradient descent. In the context of machine learning and neural networks, we typically refer to it as learning rate. That means like how fast do we step down? But again, mathematically, it's nothing else but the step size of gradient descent. However, again, in the context of this class and probably all machine learning classes, we will call it learning rate. That's just what everybody calls it. Okay. What does it mean? Well, small learning rate means we're doing smaller steps. Big learning rate means we're doing bigger steps. But we do not change the direction here based on the learning rate. the only thing we're doing here is changing how fast we're going down. We'll later see what the implications are between small and bigger learning rates. I can already say this, choosing the learning rate is a difficult problem. That is one of the most difficult things we have to do in practice. Good. So now we have this optimization, right, that we want to solve with gradient descent. So we have our given inputs x and y. Let's say we have a one-layer neural network with no activation, just a linear model, right? We have f of theta of x is equal to wx, right? That's our matrix notation. In this case, our theta is the w's. But again, I want to mention that theta will also include the biases. Like, just for convenience, I've sometimes not written it here, but always be aware when we're optimizing for a neural network, we're optimizing for the weights of the neurons as well as the biases of the neurons. Right? We have one bias per neuron, and number of weights per neuron is dependent on how many input channels we have on a neuron. Okay, so let's have a practical example. Let's say we have an L2 loss here. We want to compute it between the predictions of y hat and y, and we want to optimize for theta. Right? So we just want to optimize this function. Okay, we do have the compute graphs. That's also something we introduced. So we have x times our weights. That gives us like this output here, right? That's x times w. And then we have y, that's here, and we're feeding this into our loss function. The idea now of finding better neural network weights is now we want to compute gradients, and that's what we've done, right? We want to do gradient descent with respect to our thetas. And this is the reason why we introduced these compute graphs. Because of the compute graph, it's actually very nice to compute kind of a gradient flow. That goes from here and then goes to here. This is the process called backpropagation, which is mathematically speaking simply applying the chain rule. And the chain rule just says, yeah, you know, we can take the gradients from here. Based on this operation, we can update the set of gradients and so on. We'll go over this in a few seconds. Okay. Yeah, in this case, in the linear model, it's actually relatively easy to do that because it's a linear model. We can simply compute the gradient analytically. Right? We have an L2 loss here, so we just end up with a gradient like this one. We've done this actually in the recent lecture. And yeah, we would in this case, we just have times xt, right? That's pretty straightforward. Now, for a real neural network that is not just one layer and with activations, so we have multiple layers with activations in this form roughly, the gradient is a bit harder to compute. And this is what I said, we need to propagate the gradients from the end to the first layer, right? So we're starting from here, then we're feeding gradients here, 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 okay? And how does this work? Well, we're applying this chain rule, and this is the backpropagation algorithm that we would like to look at. In this case, yeah, we're taking this compute graph. So now we have here x, w1 times maximum operator times w2, and then the loss function with that, right? In this case, the flow of the gradients goes all the way through here. Again, just to clarify what we're optimizing for the w's. X is given and y is given. It's our training data. X and y is given in our training set. Right. So, based on that, we can now think about how can we do this propagation from the gradients. And this is the backpropagation method that I mentioned, which is based on the chain rule. And now these compute graphs become very, very handy. And I would like to go, yeah, I don't think we're going to finish this today, but this is one of the key things now. How do we use these compute graphs to do gradient descent? Why do we do gradient descent? There's a few things why. One reason is if these networks become pretty big, it turns out gradient descent works pretty well. The second thing is it's very easy to do with these compute graphs. And the compute graphs just naturally come out of the neural network. Like there's two things you could say, like, oh, well, we're using compute graphs because gradient descent is easy. But I think the truth is actually like we can reformulate neural networks as compute graphs. And because of that, we can use gradient descent. At this point, before I'm going into all the details right now, how we, how we do, the gradient descent computation, how we do backpropagation and so on. I would like to highlight, for many problems, gradient descent is not always the best option. And there's a lot of optimization strategies. And there's not just one method for optimization, but there's a lot of literature about optimization. Just to clarify, optimization is a thing that has been introduced for basically the last few thousand years, right? Like, beginning of humanity, mathematicians have looked at optimization. And there's a lot of different optimization procedures. Up to today, is a lot of things that we use in computer science is not always gradient-based. There's other ones too. There's more complicated ones. But even within the class of gradient-based optimizations, we have things like Newton's method, we have LBFGS, we have adaptive moments, conjugate gradients, and stuff like that. There's a lot of these methods. The interesting thing about neural networks is the simplest one, the SGD, or the gradient-based, the simple gradient descent-based ones, these seem to work the best. We will have a bit of a discussion why we think they work the best. And when one part is due to complexity, computational efficiency, and data size and so on. But I would like to highlight there's many optimization methods. And by no means can anyone claim today that the ones we're doing right now are the best. However, in our empirical results, by ours I mean the research community, gradient-based ones with gradient descent works pretty well. Okay, I would like to give a very brief summary about the things what we've done today. So today we talked about neural networks as computational graphs, right? We have seen we can go very easily from a single layer neural network or a linear case with activations to many layers, right? It's very straightforward. And we also have seen how we can phrase these as computational graphs. We have seen how we can evaluate them. This is the forward pass. That's what's the one thing we've talked about for a couple of times. And the goal now for the training is to find the weights, including the biases, right? Oops. And yeah, that's something we're going to talk about in the next lecture a little bit. How do we do the gradient-based optimization with backpropagation? We will see that the compute graphs are very nice abstractions of the chain rule, right? And that's where I'm going to stop today. We will in the next lecture talk about the backpropagation, as I mentioned it, and we will then optimize kind of our first neural network. And hopefully, you enjoyed it as much as I did. I would like to highlight again that we are uploading all the material to the website. We are also uploading all the material to Moodle. So either way, you can access the material. I would also like to highlight that we might want to post some information regarding the exercises. There are still some things we are currently developing. All that information will be posted on Moodle in the website. What's very important, I think, is if you have any questions, you can ask questions via Moodle, or you can ask the respective TAs. We have office hours. Again, information is being posted. You can just look that up. We would like to make sure that even in the difficult time right now that we're still having home office and so on, or home virtual lectures, we want to make sure that you're being that you stay engaged with the lecture and you're fully having as much fun as I do right now when I'm recording this lecture in my office. Other than that, I hope we see you again next week. And otherwise, stay safe and stay healthy. See you next week.